Welcome back. This is the day the Lord has made. Let us rejoice and be glad in it. In this video, I'm going to talk about things that influence the speed of a wave and talk about how this connects to things like guitars and piano strings. So, in general, the speed of wave is influenced by a couple different things. Again, we're assuming not light. So, a typical wave here on Earth that needs material. The restoring force and inertia. The restoring force is how quickly the matter can return to its original position, how quickly you can pass energy on to someone else. So if you're a solid, your neighbor's right next to you, so you just quickly pass energy on to the next neighbor, and you're back to where you start. Gases are really far away, again, so they don't have a neighbor, so it takes a long time for them to transfer the energy and get back to where they were before. So for solids, they have a pretty large restoring force. Inertia is how heavy it is. So if it's a really heavy material, it slows the wave down, which is to say that in corn syrup, a wave would travel slower on the surface than it would in water. Or mercury, who is really dense, waves would travel really slow. Now, when it comes to like guitar strings and piano strings, there's an equation that basically helps us take into account this ability of the restoring force and the inertia, which again is the density. The speed of the wave, the velocity of the wave, is equal to the square root of, well, what's the force of tension? And that's the idea of this restoring force. And the linear density, which is just how thick is the string. So when you can think about a guitar string, the thicker the string, the lower the note it plays. And so that lower note is because it slows the wave down. All right, so again, this is the equation for finding out the speed of a wave. Now, to actually connect this to the pitch, then, when you think about the pitch actually played, it comes down to how many times the wave reflects. So what's going to happen on a guitar string is the wave's going to travel down to one end and it's going to bounce back. And so the amount of times it does this per second would be the pitch. So again, how many times per second does it go back and forth? Which then, because we got to go twice the length, the actual note heard, again, the fundamental frequency, as denoted by F here, this is, again, the frequency, depends upon the speed of the wave and how long is the string. And so when you play guitar, what do? You change the pitch by, you can either tighten it or loosen the string to change the tension. But when you're playing, actually, you just change the pitch by grabbing different places on the guitar to change the length of the string. Because if you change the length of the string, that changes what pitch is heard, because it's going to go down and back faster. So, again, some sample questions connect to this. If we had a guitar string with a certain density and a certain force of tension, we could find the speed of the wave using our equation. So if we had a 1600 Newton force of tension and a linear density of 1, the velocity would be just square root of 1600 or 40 meters a second. Now, if we wanted to find out what pitch that'd be, we'd have to find out how long the string is. So if we had used that same guitar string and we had a length of 25 centimeters, we just have to plug it into this next equation, which takes into account the idea that the wave has to go down and back, and the amount of times equals the pitch. So if the wave is traveling at 40 meters a second, and it's got to go down and back, and it's 0.25 meters, it's going to go a total of down and back times of 80 times, so 80 hertz. And the big idea is the wave travels down to one end, reflects back on the other side, and the amount of times it does this back and forth would be the pitch. So again, this is generally how, some big ideas connect to the speed of a wave. Most importantly for you guys, these two equations here. This first equation helps you find out what the speed of the wave is. The second equation will help you connect that speed of the wave to the fundamental frequency.